So hello everyone, thanks for joining this week's seminar. And I'm pleased to introduce today's speaker, Professor Shengwei Wang. Professor Wang is a chair professor at the Hong Kong Polytechnic University with the Department of the Building Environment and Energy Engineering. Professor Wang is also director of the Research Institute of the Smart Energy. Professor Wang's research focuses on the optimal control and the system optimization of air conditioning system diagnosis and commissioning, energy flexible buildings and smart building technology. Professor Wang, he has extensive experience in the successful energy optimization projects, both for the new buildings and the existing buildings, including commercial and industrial buildings. So Professor Wang, so if you're ready, you can start, and we look forward to your talk.
Thank you so much. It's really my great pleasure to have the experience to share my views and research experience with friends in Cornell University. And actually, if I know the traveling is so convenient as a user today, I would prefer to personally fly to Cornell and to exchange with you in person. Yeah. So today, my topic of sharing is smart, energy efficient, and grid interactive buildings, and particularly for the technology development and some benefits in applications. So before I talk about the research issues, let me give a little bit introduction on the research institute and the research group that I'm leading. So here I'm leading a research institute called Research Institute for Smart Energy. And this research institute is established as a cross-disciplinary research platform in the university for developing innovative energy technology, sustainable and carbon neutral solutions. So actually, our research institutes, the main focus area of the research institutes, including 5 focus areas, including digital energy system and smart grid, smart buildings and smart energy systems, advanced energy storage technology, advanced and renewable energy conversion technology, and advanced energy materials. So those 5 focus areas are associated with smart energy system technologies, serving energy system and service industry, and enabling, I name it as enabling energy technologies, serving energy production industries. And the Research Institute is a university-level research institute in PolyU, which involves about 60 professors and faculty members from 12 department university. And if including research staff and research students, there will be over 300 people involved. So talk about my research team. I name ourselves to be a building energy and automation research laboratory. And our goal is to develop and apply advanced technologies for smart, energy efficient and energy flexible buildings towards carbon neutrality. So if we very quickly talk about what is the area of research. So actually, personally, I have the thermal science background in education, but my research is very much related to building automation. So when we talk about basic technology involved, so we talk about we very much rely on control technology, data analytics, uncertainty analysis, IT, and IoT technologies. So you can find that the research is mostly multidisciplinary research. So in terms of technology outputs or the technologies concerned, so we the technology we develop are concerning mainly the control application, optimization, system optimization, diagnosis, and commissioning. So in terms of the systems and the buildings involved, basically we concern non-residential buildings. So that is the different type of non-residential buildings. And if more focused, then such as zero and low energy buildings, clean room air conditioning systems, data center cooling systems, and we also research on energy flexible buildings, smart energy systems, and microgrid and district cooling systems. So you can find that we have a rather big coverage, but basically we talk about energy systems. We talk about the automation, the control of energy systems in terms of control optimization, system optimization, and diagnosis and commissioning. So then, so actually what we are working, we talk about energy efficient buildings, we talk about smart buildings, we talk about energy fast buildings in the last 10 years. So carbon neutrality, transformation of power generation is actually a key task for carbon neutrality target. For instance, in Hong Kong, the carbon emission of power generation actually contribute to 60%, over 60% of the overall carbon emission. And among this 6%, over 93% is the contribution of buildings. And worldwide, I think you know better than me, it's over 40%. If we talk about the mainland of China, is the over emission of buildings is over 51%. So talk about the regular pathways for the carbon neutrality in power sectors and the key problems. So traditionally, we know if we want to achieve carbon neutrality, then we have two means. One is the energy efficiency in the demand side to reduce the energy demand. And another means is to have more and more renewable generations at the supply side, and also probably also in the demand side. So that will help to solve the problem to achieve the target of carbon neutrality. But in the last few years, we actually realized that it's not just so simple to reduce demand and increase the renewable generation supply side. But actually, due to the more and more renewable penetration, there's great challenges of supply and demand mismatch. So we got to solve another problem of the supply and demand mismatch. And if we do not handle it properly, there is big issues, including the increase the rate of renewable curtailment, increase the stress on the power grid, energy balance, and reliability, and even more serious cases, the risk of power grid blackout. So then the regular solutions to solve this mismatch problem is to significantly increase the storage capacity for power balance. So that means grid investment and practical limitations. And the basic means is to invest the power pumped storage, battery storage, and the green hydrogen. So that is the basic means. Those means technologies are very effective, but it's rather expensive and sometimes technically or environmentally limited the development. So therefore, we got to look for more effective and low-cost alternatives. So that is actually in the demand side for buildings as the main consumer in the demand side. Then we have contribute to the power grid balance and reliability in a more cost-effective means. So that it means the buildings not only increase the demand side efficiency, reduce the load, and but we can also increase the energy to contribute the energy flexibility, to to contribute the power balance, and also, of course, to reuse more and more renewables in the demand in the buildings. So therefore, energy flexible buildings and grid interactive buildings or grid responsive buildings. So actually, it's the new term, and this is a new means for buildings to contribute to the carbon neutrality goal. So for energy flexible buildings, those buildings which can reduce the power use without unacceptable compromise in service quality when the power grid is short of power, and stored energy, and when there is surplus power in the power grid. And so actually our research, in Hong Kong is a huge, very high density areas. So, and our focus is more on the high density cities. So for the high density cities, how to achieve carbon neutral transmission of power systems in those high density cities? So that is a big challenge. For instance, in Hong Kong, Shenzhen, or in those big cities in the Great Bay Area and in South and East regions of China. So, but what are the contributions? And actually, for the contributions, basically is reduce the energy demand, enhance in grid power balance for higher renewable penetration. In the buildings, the particular high-rise buildings in high-density cities, and there is very little chance for us to adopt to renewable energy generation, such as solar PV, such as wind power. It is almost impossible, or it only can have a very little percent of renewable energy can be adopted. So then talk about the grid power balance need in different tempo scales and the potential contributions of power flexibility, of building flexibility. You can see this is a show of the different flexibility services which is needed for power grid. For instance, faster regulation and moderating regulation. So that is very fast. Talk about in terms of seconds or minutes response. And for the slower or the big scales of services required by balance services required by power grid, such as node shifting, node shifting, and even node coverage. So that is takes something between minutes to hours. And for those node covering, that takes the period of months. So it is typically for buildings, it's not so capable of providing this service because of the storage capacity of buildings is limited to provide such a service, require a very large storage capacity. So then we talk about what is our research and our contributions in the demand side flexibility. One of the basic work we actually do is to demand side flexibility categorization. For instance, we talk about what we can contribute to the power system balance and reliability for more renewable penetration in the power systems. So then we talk about fast regulation, moderated regulation, node shading, node shifting, and node coverage. So from actually you can find out from in buildings, we can respond very fast to the power systems from seconds to minutes, and we are very good in response to demand of power grid in the scale of minutes and hours. So that is, and we can actually have much cost-effective contributions for the service of increased power balance of power grid, of the power grid. So this is the energy quantification index we developed. We actually propose a 5-dimensional radar chart to graphically represent the effective performance of different typical surfaces, including the absolute flexibility capacity and the flexibility ratio of buildings. And we talk about energy flexibility technologies for contributing to power grid balance and high renewable energy penetration. For instance, we developed the control methods for building HV system in responding to urgent demand reduction requests from smart grid. So this is what we have a look on the conventional feedback control and the building demand response methods. So for the conventional ways, actually we can do rather conveniently. So for instance, we increase in the case of cooling systems, if it's heating system, we just reverse the control. So in the case of cooling system, if we increase the set point of space, then the cooling demand of buildings can be reduced. Then the cooling supply of HV systems needed can be reduced, and eventually we can reduce the power consumption of HV systems and buildings. But this way is rather easy, and actually the control of the conventional control can support this. But so the advantage is no additional thermal storage is needed, and we can actually have the original cost saving, and conventional control can be used. But the challenge is very slow in response. So it's only applicable for scheduled requests or requests informed well ahead. So if the power grid have a very urgent response, and we have to respond very quickly, very fastly, and then in such a case, this kind of control doesn't work because the response is rather slow. So then we developed a fast demand response method by directly reducing the cooling supply. And we talk about direct load control from the view point of power grid. So in such a case, actually, it's a proactive method, and we can directly reduce the power consumption of chiller plants in the central. Then we can then at the same time we decrease the cooling supply and decrease the of chiller plants and decrease the cooling supply to buildings. And then eventually the indoor temperature will increase. So with some sacrifice of thermal comfort, then we can reduce the building demand, building load to respond to the request of power demand reduction from power grid. So in such a case, actually it's very fast and almost immediate response in terms of seconds. It very much depends on how information is transferred from power grid to buildings, and the response of building control systems actually can be handled within a few seconds. And but the problem is the conventional control cannot control the system properly, and the system will have disordered cooling distribution. So that is a problem. For that, we develop methods to handle these problems. We developed a solution is the cooling supply-based feedback control for fast demand response of buildings to smart grids. Basically, we developed distribution methods, use the feedback that is the temperature, the average temperature of different rooms, and based on the average temperature of rooms, we feedback to distribute the limited cooling supply using a cooling distributor at the high level. Using the cooling supply at the distributor at the high level to distribute evenly as needed at a high level to different zones. Then we, at the lower level, local level, we have another level of cooling distributor to distribute the limited cooling supply to different spaces to allow the cooling distribution at different zones is evenly distributed with even comfort satisfaction sacrifice, and to allow that the buildings can have a reasonably long period of demand reduction as expected by the power grid. So these are the another technology we developed is the smart control of HV system of enhanced building environment performance for providing frequency regulation services to smart grids. So this kind of service actually in Hong Kong is not yet in the market, but in some European countries, in some states of in the US, so this is service is actually available in the electricity market, and the user side and the demand side can actually provide this service to power grid and with some return in terms of economic return from power grid. So let's have a look. Actually, by having the information from the power grid, such as different power market may have different ways to handle, but basically is the power grid will have given information to the demand side through the communication systems, and then if the buildings actually have the agreement with the utilities, with the market operator, then we can provide the service and we can manage the demand and the load of buildings in response to the following the control signal of the power systems of our grid. So the main problem of providing these services to power grid, one problem is if we can provide we can control the building system to provide the service timely to as required of the right quality as required by the power system. Another important issue is one, we provide the service and there maybe have a significant impact on the environmental control quality of the building systems. That is the first problem. And the second, another problem is because this control disturbance is introduced to the building system, such as air conditioning system, and that may cause extra damage of the power system of the building systems because of more frequent regulation and action of the control devices. So therefore, we introduced we developed a control enhanced with disturbance compensation for providing power grid frequency regulation services. So so this is this part. So this is a frequency disturbance compensation. The key point actually, if you are familiar with the control methods in the control discipline, you will find the disturbance compensation method is a very typical means for enhance the control performance of the control loops. But in their case, there are two issues. One issue is to identify what are those unwanted disturbance, and the second is to find the methods to compensate the impact of those disturbances. But actually, in the frequency regulation control of buildings to provide the frequency regulation service to power grid, actually this disturbance to the air conditioning system control is actually generated by ourselves. So we know what is the disturbance we have. So we know this difference. If we develop a method we call frequency disturbance compensation scheme, so then we can compensate this disturbance to reduce the impact of this disturbance on the air conditioning system controls. In one side, that will can significantly reduce the impact to environmental control quality, and another is reduce the wearing those unnecessary control actions, such as the moving of the actuators, and to reduce the wearing, the damaging potentials of air conditioning system in operation. So some other ongoing research my team is doing is smart and economic control of hybrid building energy systems and building clusters or district for providing multiple grid services to power grids. So here I very quickly show you what we are doing without the details. For instance, grid flexibility service involving hybrid building energy systems. What we are doing is to optimize flexibility allocation in the buildings to provide grid service in the best manner, and to maximize the economic benefits of buildings in providing grid flexibility services. And another area we are working is the life cycle economic analysis of storage systems in buildings or in building district to provide multiple flexibility services. Here we optimize the dispatch of different storage systems and identify the optimal configuration of hybrid storage systems. Here we talk about new building development, and we also research on how to enhance the existing buildings, and including the building the district or building clusters. And another area of our research is to business development for unlocking building energy flexibility towards multiple flexible services. You know, for the moment, I think in different countries, and particularly in Hong Kong and in China. So, for instance, our research in my team is actually we started energy flexibility research, building energy flexibility research for 10 years, but actually the development of power grid for engaging the building demand side flexibility is rather new. So we got to, our research also helped the power systems and to develop business models and how to engage the demand side flexibility services in effectively, and to have mutual benefits for the demand side participants and for the power grid. And energy efficiency and smart building technologies is a long term, and we're actually working in this area from the starting of my academic career and from the starting of my research team. So here I talk a little bit on what we are doing and what we did for smart and energy efficient building technology for reducing energy demand or reducing energy use in buildings. So, so I talk about the latest efforts. So I use an example of large projects we got from the government. So that is to develop development of next generation key technologies for smart buildings. And so this is an ongoing projects, and this is almost is cover many of our current research, ongoing research activities in the research team. So here we develop the technology in 4 layers, including fundamental technology to study the dynamics of emerging and integrated energy systems. And we also develop platform technology to provide seamless field control network based on IoT. And we develop fundamental technology, including distributed real-time optimization and big data analytics. And in terms of application technology, we develop health monitoring, diagnosis, and real-time control optimization technologies. So, and the research objective and task and deliverables, and we group the research deliverables in 3 main areas, including field level IoT implementation and optimization, and big data analytics-based building health monitoring, diagnosis methods and technologies. And we also developed advanced control optimization method and technologies. I show you a little bit what we did. So in terms of field level IoT implementation and optimization, you know, today's application of IoT technology and in buildings is basically effective way, a low cost means to collect the information from the field, and this information will be transmitted to the cloud to make decisions, and those decisions mostly are not time critical because we send it to cloud and we make decisions and send it back, and we cannot make the time critical solution decisions, and which have to respond very fastly. So it's not possible. For our development, is actually to develop, we developed the IoT-based field control network or systems using wireless networks for HVC field optimization. And we also developed IIoT, so that is in industrial IoT-based field control topology and architecture based on 4G and 5G cellular networks for time-critical HVC process controls. So this kind of controls is traditionally is people, the expert are considered to be impossible for IoT to technology to provide this kind of time-critical control applications. And another area, area we develop is distributed optimal control methodologies for HV systems. So the basic idea is that you know, the optimal control mostly today we have to collect information from the field control devices. We need to send the information, the data to the higher level, and to make control optimization, because the local control, one side local control computational capacity is not do not support. Another is the program environment cannot support the very complicated optimization software or the routines to be implemented in the field level. But if we make use of the distributed computational resources, such as the IoT devices and or the field control systems. So how to use this kind of control as the resources, computational resources in the field level. So we developed such distributed optimization methods for building systems. So one thing is we got to decompose, to break those large optimization problem into sub-problems of small scales. And we develop effective and robust online optimization actions that we can use those distributed computational resources, such as IoT devices, such as the field controllers. So then we allowed this problem to be distributed to different controllers, IoT devices. We coordinate those routines distributed in different small field devices. Then if we can ensure the convergence and ensure the tolerance and use kind of agent-based or event-based controls, and it allows this kind of big optimization problems can be handled in distributed IoT devices or the field controllers to achieve the distributed optimization of HVAC systems particularly. And we also developed a big data analytical framework based on the domain knowledge and machine learning for analyzing big building operation data. So we integrate building information, that's BRM, and IoT and building automation system information to provide the health monitoring and diagnose functions for buildings. So actually, this work is led by a young colleague in the team, and develop automated data-driven health monitoring for diagnosis strategies for air conditioning systems also. And we also developed advanced control optimization methods and technologies. For instance, we developed AI labeling, enabling smart fare controllers for integration with conventional building automation systems. So here, this is the controllers developed. Actually, we can the AI software tools routines are actually embedded in these controllers. Then this controller can integrate with the conventional building automation systems through the open network protocols. So we also developed a real-time optimization method for closed system coordination and building grid response. And finally, I'd like to report to you that as something proud for my team, and so we have close link and a balance between academic research and industrial applications. So you'll find in terms of academic research, in terms of engineering practice, for instance, we have over 30 million industrial grants and technical awards, and we achieved quite many building application projects. We achieved saving between 15% to 42% energy savings in actual buildings. So here I show you that is what technologies we developed based on the research outputs. We have developed a system approach towards energy efficient buildings. The technology supporting design stage, supporting the work in construction and T&C stage, and operation stage for optimized operation and control. So here I summarize the tools we developed, including the virtual test platforms to test the system design to optimize for the optimization of the system design, and also to test the optimal control strategies to be implemented in building automation systems. And we developed the energy diagnosis tools, and we also developed the optimization tools, including system optimization and including the control optimization. And so here is some examples of practical applications and energy benefits. For instance, this building, we help to optimize the air conditioning systems, to optimize the instrumentation of building automation systems, and we help to develop and implement the energy optimization strategies in buildings and save the energy. This is the tallest building in Hong Kong, and we can help them to receive the energy, the electricity of over 10 million kilowatt hour per year. So that is equivalent about 18% of energy in the buildings. In a hotel, we help them to optimize the energy system, optimize the control, and achieve the saving of 25%. We also helped to develop the underground station air conditioning validation systems, and as a new generation of air conditioning system and controls, and achieved a saving of 30%. So in industrial building for pharmaceutical manufacturing, so we optimize the energy system control strategies and help them to save over 40%, actually 40% of the energy use in buildings. And in the campus of the university, we have many applications. One example is actually for one phase of the building, we contribute to the actual saving of around 38%. So actually, the project is ongoing. So we just have agreement in over the last few months, just a couple of months ago. We have a new big applied research agreement with a company for the development of new commercial complex atop of the Kalong high-speed train station. So we actually implement the latest version of smart, energy efficient, energy flexible building technologies in that building to develop the smart, energy efficient and energy flexible buildings. And this is actually will be the first large-scale energy flexible buildings in Hong Kong. And we hope by this means those high-rise buildings can actually contribute to the carbon neutrality of the power systems by supporting the power grid to absorb the more renewable generations such as solar and wind generations in a different site rather than in buildings in the center of the cities. So this is what I like to share with you. Finally, I like to welcome all of you to visit Hong Kong and to visit the Hong Kong Polytechnic University and the Research Institute or Research Institute for Smart Energy. And actually, the university do give me as one of the target for international exchange, and the university actually do give us the funding support to support international exchanges, the inbound visit from overseas, right? And the university also welcome the exchange of PhD students in short term, in a longer term, for instance, 3 months and 6 months. And our graduate school actually have a program, a financial support program to encourage this kind of exchanges. And finally, I also welcome young colleagues and young friends to join the Hong Kong Polytechnic University if you like to work in the east part of the world. And actually, when I joined the Hong Kong Polytechnic 30 years ago, and my friends in US asked me, so you go to Hong Kong, can you still continue to do research in Hong Kong, in the universities in Hong Kong? So it's rather a big question, right? In Hong Kong, can we do research? Is there sufficient support for us to do research? Actually, after 30 years of experience in Hong Kong, and you can see that in Hong Kong, we have environment, we have funding support, and to support us to do research as what we like. So this is what I like to share with you. And I think we do not have a big team. We have a tiny team. So I'm happy to have a more close exchanges and communications. And so if you have some questions and if you have some suggestions or comments to me, you are welcome. Thank you.
Thanks, Professor Wang. So thanks, Professor Wang, for the last talk on the smart, energy flexible, and energy efficient buildings. So now may I invite the audience to ask questions if you have. So for this, yeah, Tianqi, you can unmute yourself.
Thanks for your impressive presentation and talk, Professor Wang. And I may have some little questions. So the first question is that I see several of your applications to the rail system in Hong Kong, and I think they are very exciting. But I want to know that what difficulties were you facing when you want to implement your method into the rail system, like the grid interactive technologies or other technology, what the actual difficulties?
So I tell you the truth. I joined Hong Kong in the university. I start my career in that time. Probably I was as young as you today. And in the early career, I say, okay, we do energy research and we do building research. We got to cooperate with building owners and developers. So I go to visit them, and they tell me that, yeah, your technology, your research is very interesting, but it seems it's very nice academic research, but it seems to me that we do not need it for the moment. So that is 30 years, 25, 30 years ago. But I fear that the big change in, say, about how long, 15 years ago or a little more. So then, because the industry feel that energy efficiency, reduce energy consumption is very, very important. So then we worked with them, but in the very early stage, you are fine. My first big scale application is because the user, the developer want to show that they support the industrial research in university academic research, to show their contribution to research. So we did, and 1 week work with them, and they actually assigned one PhD graduate as an engineer. They have an engineer with a PhD degree. They use this one as the interface with us. They think because this group of academics may make troubles to them, so they have a buffer. But when we work with them, they find out this research team, like me, we are not pure academics. We know where the real system, real problems. Then we can actually have the same language and helpful to the practical problems. Then we got their trust. The first one is rather a challenge. When you have the records, the track records, then if the record they will trust you, and so many of for we are doing building energy system research for big energy systems. If we test our technologies, test our ideas in laboratory scale, it is not so meaningful. So we got to test it in real buildings of large scale is more meaningful. So actually today, after so many years of experience, collaboration, and we got the confidence, our partners have confidence. So if now we propose something to test in real site, have no question, because we know the practical limitations. We know what can be done, what cannot be done in the real systems. So then if we propose some new test and a new technology to be implemented, so mostly we have very positive support from our industrial partners. So the first trial and the first track record is very important.
Yeah.
And we need to know the real problems and real situation.
Yeah, thanks for your answer. And another question is that I have read several of your recent papers about data center modeling or applications. And I'm wondering that if there are any, prospective applications of data center compared to the other commercial buildings in the application of grid interaction or the carbon neutrality, especially when we want to involve some artificial intelligence or big data analysis methods into the energy management system problem.
Thank you. This is a really interesting problem to be addressed. And we do, the problems of the tools, if you, for different buildings, are actually have some common. If you can solve the problem here, and you can, it's also help to solve problem in other places. And what we are doing now for data centers is we help them to optimize the design and the configuration of building systems to try the best to have free cooling. That's one side. In another side is we are working on the data center energy management, because one, if we work alone, we think we do not feel that some of the operation of computation in the data centers actually can be manageable. Some of the computational load or data processing load is you cannot change. It's rather, but some of the load is manageable. It's more flexible. So we can actually, through the management of the data centers, data processing node, that is one way to manage the profile of energy consumption overall. That of course also including the cooling demand of data centers. And then another means is actually in data centers there is a inherent storage in data center, and this storage is that is the UPS system. The UPS system is providing the safety operation of the data centers, but really activated in real situation. So if we can better use this system, that also can provide us the possibility of optimizing the optimization of the centers. So we need to cooperate with different teams in data centers.
Yeah.
Thanks
for your answer, Professor.
I think there's a question from Mary in the room. So Mary, are you able to ask the question directly? You can unmute yourself and ask the question to Professor Wang, if you can.
Okay, I'm unfortunately not able to get my video started, so I apologize for that. My question, Professor, is first, thank you very much for your excellent presentation. This might be kind of a big question to ask, but what do you see as the potential, if any, for artificial or augmented intelligence to streamline prioritization of distributed, local versus centralized decision-making in smart grid systems for improved performance?
Yeah, this is a very important and interesting issue. And actually, in my team, we have two senior academics, myself and another younger colleagues in the team. And my young colleagues in the team actually pay more efforts in leading the AI-related research in the team. So actually, I'm rather positive and critical to the application of AI in building systems. So actually, I'm the first people always challenge the AI-related research, including the data-related research. And I think one of the important things is that, and I also have many communications my friends in the building area. Many of us are related to optimization and automation. And so therefore, we are very close and we are very positive to AI applications, but we are also very critical to AI applications. So my ideas is AI must bring something to the advance of building automation, because in buildings, we are so many, for building automation, and optimization. There are so many data need to be handled. The data are available. But another thing is that I do not think AI can solve everything, or AI can solve many things, because many of our applications problems in buildings, we have a rather reliable and effective way to handle the problems. But with some of the problems, actually, for many years, we cannot have a good solution, effective solution to that. And for that areas, AI may have a good chance. So that is my ideas. I see in our team, we do in a few areas, and I see the benefits and the advantage of using AI, using data-driven methods. And so it's positive, it's encouraging, but AI cannot solve all the problems. And I think for the experts, I think today, I'm not quite sure today, we should not be driven too much by the IT experts, because IT experts think if we provide data to them, they will give a solution through big data analytics or through AI. But actually, the data expert need to work with the domain experts to develop a real effective, reliable, data-driven solutions for building application.
Thank you.
If I'm not sure if I answered your question. This is a very big question.
Yes, yeah. It is. It is. Thank you very much. I appreciate it. And I know that we have limited time, but it just occurs to me that possibly AI's potential might be on the softer side of the system rather than the quantitative side of the system, meaning where there's a human interface, it might be able to expedite that decision making, but it's going to take a lot of effort to get there, and it's going to take some good brains to achieve that. So thank you.
Thank you. Yeah. Professor Wang, myself also has a question on the energy flexibility for the buildings, for the grid. So you mentioned that you have done some work to on the building energy flexibility to provide some services for the power grid. So because the power grid sometimes is a very large scale, so in order to provide the service for the power grid, usually we need to like utilities of the large scale of the buildings. So just wondering if you have verified the benefit of the building energy flexibility with some power grid model.
Yeah, and actually, you know, if you talk about individual buildings, even these huge buildings, very large buildings in Hong Kong, compared with power grid is very small.
Yeah.
And but when if you consider the buildings together, so it is a very huge part of the compared. It's rather comparable. For instance, in Hong Kong, the energy consumption of a power grid is actually 90% is consumed by buildings. So therefore, building means a lot. And but the problem, the situation is the building are small individuals together. So therefore, if we want to encourage buildings to be involved, to provide the flexibility service to power grid, then we need to have some effective means to encourage. For instance, it's very hard for the power grid to have individual contracts agreement with individuals, but they can. The conventional way is to design certain energy policies or the pricing. And so therefore, And this pricing and the policies can be can be designed in a smart way, so that can actually to be beneficial to both sides. So I think the pricing and the market mechanism is very, very important.
Okay, I see. So it's we show some great signals to enable buildings to regulate their demand.
Yeah, and the grid side or the power market side, the electrical market side, will have some online computation to determine at this moment or sometime later what are the incentive or what are the price given to the users, and the users inform the users, and then the user can actually have some benefits, some incentive to be involved to contribute. So actually, this is still a new place, and so how to design and what is the mechanism and how to design the incentives or energy electricity price is also one issue for research.
Yes, I see. So just wondering the demand response building control this kind of technology this technology has been implemented in some real buildings in Hong Kong, or is it still like under development stage?
Just a few months. I think, for instance, in Hong Kong, we do research in this area for 10 years, and but at the start, is not much people do it, and also no application, because right. So in recent years, we see the application, and we see the interest of industrial partners, and it's just starting. And because the design of the electricity pricing in Hong Kong for the moment is not provide much as incentive to the participation of demand side buildings to the flexibility service. In states, you have more. In some states in the US, in European countries, some European countries have it's more mature electricity market. And in the mainland of China, in the last 2 years, it's quite fast in introducing flexibility services by the power system, power grid. Yeah, I think the chance of application, the benefits of building to participate in the power system flexibility service is increasing very fast in the next few years.
Yeah, I see.
Because more and more renewable generations getting introduced to the power systems in different countries.
Yeah, I see. I think in maybe in the near future, if we have more real world applications of this.
Yeah, in Hong Kong, actually, we actually encouraged the. I presented the last project to you, and our partner are convinced to invest. It's a rather not huge, but rather significant investment for flexibility and for building flexibility. And we can, for the current pricing of electricity, there's reasonable return. But if we consider the future need, demand, the incentive for demand, flexibility participation of buildings, the benefits of buildings will be more. So then actually, because two reasons. One is for the moment in the current pricing, it is marginally beneficial for buildings to introduce energy flexibility, and consider the middle term market change. So then our partner is rather positive to invest flexibility. So therefore, we actually work together with our industrial partner for a rather, it's a very big building project to introduce building energy flexibility.
Yeah, thanks for the answers. So, any further questions for Professor Wang? If no further questions, thanks again for Professor Wang's last talk on the smart buildings. Thank you.
Thank you. So finally, again, welcome all of you to visit us in Hong Kong and to the Research Institute.
Yeah, sure.
Thank you. Yeah. Bye-bye.
Bye.